Pretty fast.
Okay, I can think fast too.
One reads a plus 5 microcoulomb charge rests in the middle of a hollow sphere whose radius is 2 meters. The charge of minus 5 microcoulombs is placed on this sphere. Determine the electric field 1 meter away from the sphere center. That's inside the sphere. So we have basically a metal sphere with a charge dead center of plus 5 times 10 to the minus 6.
Oops.
And we have a sphere with a charge of minus 5 times 10 to the minus 6. What we're going to do is put a Gaussian surface at the 1 meter mark. The whole distance is 2 meters. And we know that the integral of E dot dA over that entire Gaussian surface must be the total charge enclosed, which is 5 times 10 to the minus 6 over epsilon. E dot dA is constant over that entire surface because it's going to be radiusymmetric. So we know this comes out to be E times 4 pi times 1 squared, 4 pi times r squared. That's equal to 5 times 10 to the minus 6 over epsilon, or E equals 5 times 10 to the minus 6 divided by 4 pi epsilon. You have to reconstruct the vector, so I'm going to call this direction the r direction. Make it a vector, r unit vector, and that's the answer. The minus charge on the sphere doesn't make any difference because you're inside the sphere. It's only the charge enclosed. Any questions about the problem? Okay, problem number 2. 2 infinitely long lines of charge are parallel with each other and 2 meters apart. The charge density on the line to the left is minus 1 microcoulomb per meter, where the charge density on the line to the right is plus 2 microcoulombs per meter. Use Gauss's law to determine the voltage halfway between the lines of charge. Draw a picture. On the left, minus 1 times 10 to the minus 6. On the right, plus 2 times 10 to the minus 6. They're 2 meters apart. And you want to find the E field here. Now, for a line of charge, E, the integral E dot dA equals the charge enclosed over epsilon. We're going to form a Gaussian surface like this. And E dot dA considers only the size of that, which is E, times the area of the size is the circumference, 2 pi times 1, times the length. Let's call out the L. That's the circumference, 2 pi times 1 times L, the length. That has to equal the charge enclosed, which is lambda L divided by epsilon. The L's cancel, and we end up with E equals lambda over 2 pi epsilon. It's in some direction. I'm going to call this direction the I direction. So, due to this charge, it is minus 1 times 10 to the minus 6 over 2 pi epsilon. In the direction minus I. Okay? Because since this is a minus charge, the electric field is this way. That's E due to the first charge. Let's call that E1. Any questions about that so far? Now, E2, that's due to this charge. Same answer. It's equal to 2 times 10 to the minus 6. 2 pi times 1, again, same thing. So it's divided by 2 pi epsilon. However, this is a positive charge, so E2 is in the same direction. So it will be in the minus I direction. E total is simply E1 plus E2. And that's equal to 1 plus 2 is 3 times 10 to the minus 6 over 2 pi epsilon in the minus I direction. Now, if you call that the plus I direction, your answer will be just opposite of mine. That's fine. Again, Gauss's law, you add electric fields. Draw a picture so you recognize, even though the charges are opposite, the electric fields simply add between the two. Any questions how to do it? Yes.
That second line under the integral, that one, can you read that off there?
E times 2 pi times 1 L equals pi lambda L over epsilon. Lambda is, this is lambda 1, this is lambda 2. This is simply 2, the distance between the two. Yes.
What's the positive charge actually left?
Negative 6 over
Yeah. Why is
That's good enough?
epsilon
No, I just wonder why that's
direction.
It says minus to the left, plus to the right.
Okay. I almost had it.
Yeah.
I almost had it.
Any other questions?
I got the last one right.
Okay, problem number 3. Two infinite metal sheets are charged lie horizontally, one above the other and 1 meter apart. Since if the upper sheet has a charge density of plus 4 microcoulombs per square meter, and the lower sheet has a density of plus 2 microcoulombs per square meter, determine the voltage difference between the two. The sheet on top. It has a surface charge density of plus 4 times 10 to the minus 6. You have a sheet on bottom.
We get a point for that, by the way. Remember?
Okay. Charge on the bottom is 2 plus 2 times 10 to the minus 6. Okay, you form a Gaussian surface. So, due to the top charge, you have epsilon times A. A is this surface here. You're inside the middle here. Therefore, it's simply the surface charge density is equal to charge enclosed, which is 4 times 10 to the minus 6A over epsilon. So E, do the top one, is 4 times 10 to the minus 6. A's cancel over epsilon. This is a positive charge. This is downwards. I'm going to call upwards positive J. So E1 is downwards, it's minus J. Okay? You're pointed away from the positive charge. E2, by symmetry, is 2 times 10 to the minus 6 over epsilon. It will be upwards. It's away from the positive charge, which is positive J. E total is the sum of those two, which is equal to minus 4 times 10 to the minus 6 epsilon j plus 2 gives me minus 2 times 10 to the minus 6 epsilon j. You just added those two. Now, the voltage is simply the integral of E dot ds. E is constant, so this in V simply equals E times S. S is the distance between the two, which is 1 meter. So this equals E times 1. So voltage equals 2 times 10 to the minus 6 over epsilon. No vector. The simple integral because E is constant. Volts. So you do Gauss's law again, like I told you during the thing, and simply integrate. Yes. You got it? Problem number 4. Two-point charges lie on a horizontal straight line 10 meters apart. The charge on the left is plus 1 times 10 to the minus 6. The charge on the right is plus 2 times 10 to the minus 6. Determine a position, if any, on the line other than infinity where the electric field due to the charges is 0. Okay, we got 3 possibilities. We got over here, we got somewhere between the two, or we got way over here. The distance is 10. If I'm over here, the electric field to both charges is in the same direction. Therefore, I can't get 0. If I'm over here, electric field of both is in that direction. I can't get 0 other than infinity. Between the two, the electric field to this charge is this way, to this charge is this way. So it's somewhere between the two. So let's call the position x from this one. This distance from here to here would be 10 minus x. The electric field is equal to 1 over 4 pi epsilon. Due to charge 1 times 10 to the minus 6, divided by the distance between the two, x squared. Let's call this the I direction. The electric field will be this way, positive I. The electric field due to the other one is 1 over 4 pi epsilon. 2 times 10 to the minus 6. The distance from here to here is 10 minus x quantity squared. The electric field due to this one is that way, minus I. And we want this equal to 0. All right. 1 over 4 pi epsilon. If you multiply by that, you get they cancel out. 10 to the minus 6 cancels out. So we end up with 1 over x squared minus 2 over 10 minus x squared must equal 0. Or x squared equals 10 minus x quantity squared over 2. Multiply both sides by 2, and I get 2x squared equals. I'm going to expand 10 minus x. I get 100. minus 20x plus x squared. Or x squared, subtract x squared from both sides, plus 20x minus 100 equals 0. The quadratic formula equals x equals minus b plus or minus the square root of b squared minus 4ac over 2a. Plug that in. X equals minus 20 plus or minus the square root of 20 squared minus 4ac. 2 times 100 times 1. But this is minus, making that plus, all over 2. To solve that, x comes out to be 4.14. It's a vector, and I called that the I direction. So the answer is 4.14 I, or whatever that is, 10. Yes?
Can we just, instead of using the quadratic, just plug it in our calculator and like graph it if we get the same answer?
Sure. Yeah. Just simply say solving and get this. Yes?
How did it become a 2 plus? I know how it became plus, but how did it become 2?
What becomes 2?
4AC became 2 times 100.
B squared plus AC? Did I screw this up? 4. I'm sorry, 4. My fault. Yeah, I wrote it down wrong, but the answer is the same. Okay, notice how heavy Gauss's law is used. In these problems, you use Gauss's law like a summer stick. You could have used the actual integration, you correct. Please notice how important Gauss's law is. Now, I didn't ask any definitions because you could obviously look those up. Any questions? Yeah.
On number 2, it says determine the voltage. So
Yeah.
we thought we have to find.
E got ds. That's all it is. And that just turned out to be ES and EF was 1.
Okay.
So it's numerically the same answer. Okay.